Hello everyone, this is Anas Mahmoud, and today I'll be presenting our work Dense Voxel Fusion for 3D Object Detection. This work has been done in collaboration with Jordan Hu and Stephen Westlander at the University of Toronto at the Toronto Robotics and AI Lab. LiDAR sensor provides accurate range measurements useful for the task of 3D object detection. However, the density of LiDAR returns falls off as a function of range. Here, images could help in two ways. Image features can improve object classification. This is an image of a pedestrian in two traffic posts next to their corresponding LiDAR returns. It would be very difficult to distinguish between geometrically similar objects from LiDAR returns alone, yet these objects can be easily classified from the image data. Moreover, the density of image features can improve 3D detection at mid to long range. Here we visualize two examples of close-up cropped images from Kitty dataset. LiDAR points are projected onto the image plane as color-coded depth values. Clearly, cars at mid to long range are represented with less points in 3D compared to the number of image pixels. These two examples motivate designing camera LiDAR fusion models. Early fusion methods extract semantics from 2D image-based models and add image features to the point cloud features. The enhanced point cloud can then be processed by any 3D object detector. Now, due to the sparsity of the point cloud, these methods limit the amount of information transferred from the images to the LiDAR stream. Intermediate fusion methods fuse features from image and LiDAR backbones and learn 3D object detection tasks in an end-to-end fashion. However, training is challenging due to different rates at which each modality-specific backbone might overfit. And finally, late fusion methods fuse independent detections from 2D and 3D detectors. These methods are mainly LiDAR-centric, where a missed object by the LiDAR stream cannot be recalled even if it's detected by the image stream. The main idea of dense voxel fusion is to fuse LiDAR features with image 2D predictions at the dense voxel feature representation level. The voxelized point cloud is first processed by the sparse convolutional block to generate 3D voxel features. The voxel features are then localized at the voxel center and then projected onto an image-based foreground mask to extract a foreground probability. Each voxel feature is then weighted by the corresponding image-based foreground probability. And finally, we add a skip connection to preserve features of LiDAR voxels misdetected by the image stream. In the second row of this image, we show point cloud and pixel correspondences, and in the last row, we show voxel and pixel correspondences. As we can see, dense voxel fusion substantially increases the number of camera and LiDAR correspondences. In addition, we propose a multimodal training strategy that does not require image data during training. We simulate 2D detections by projecting 3D LiDAR bounding boxes onto the image plane. To simulate image misdetections, we add LiDAR objects from other scenes to the point cloud and project their 3D bounding boxes onto the foreground mask with a dropout percentage. Here we show a significant improvement in the performance of LiDAR methods using dense voxel fusion for 3D object detection on Kitty and Waymo autonomous driving datasets for single and two-stage 3D detectors. Finally, we show that the proposed multimodality training strategy leads to better generalization compared to training using noisy detector-specific 2D predictions. Thank you.